Welcome to clickmyproject.com. Our product title is Single Bit Line 70 SRAM cell for near threshold voltage operation with enhanced performance and energy in 14nm FinFET technology. Now we are going to see our product abstracts. In this demand for energy efficient portable and battery operands of the applications increase the low power circuits D signals, and fundamentally the importance of the enhancement energy efficiency has been achieved by near and sub threshold digital circuit designs. In the sub-threshold regions, energy efficiency can be maximized, but the performance is significantly degraded of the near-threshold regions. In contrast, allow the balance between the energy efficiency and performance that the focusing of the near-threshold voltage circuit design in the NOCs of the and SOC of the concept. The SOCs with the supply voltage reduce the NTV can achieve the high energy efficiency with degradations in performance. And then the critical static random access memory cells, because these are typically designed using the minimum transistor size for high level integrations. Thus the read stability and write ability of the SRAM cells can be degraded. This will limit the NTV operations to reduce the voltage variations on the shaped field effect transistors are widely used in the sub 22nm technologies. In the FinFET reduce the random major contribution of the voltage variations using undoped channels. And in addition, FinFETs can achieve the better and short channel controllability of these thin body of the 3D structures in the SRAM technologies. Although the FinFET device provide many advantages of the 70 SRAM and 60 SRAM that be with sufficiency yield the NTV regions. In addition, it will difficultly improve the read stability and write abilities. To improve the read stability and beta ratios, which is ratios of pull down to pass gate, the transistor strength and the strip voltages of the cross point inverters, and then the ratio of the pages and the transistors in will be the cross point inverters must be with the complex of the reduce the fast circuits with the condensations of the effects. Now we are going to discuss about our product flow diagrams. So we have designed in the our processing Tanner EDA tool. So we have giving the input and input read and write. So we have write the bit for input data bits in the Tanner tool and the fit, and then we have designed the 70 SRAM CMOS design in the process. In the 70 SRAM cells we have using the different cell bit lines and the both read and write operations. On the 70 SRAM, the cell element of the read distributions of the row of select issues using the additional page transistor, and then the control the column directions. The read operations WL is enabled under the right hold line and then disabled, which decouples the static nodes of the BL. Thus with the read distributions is eliminated. During the write operations, WL and WWL is a selected column and enabled. And then we have designed the 70 memory layout design process. In the memory allocations, where the store is the node and decoupled the process BL, which eliminate the row of select issues. Although no write back scheme is recorded, in the increased cell height increase the C write in the column directions. In the process, we have designed the layout, the some write and select the off select issues and the write back scheme in the process. In additional cell areas, increase the large number of transistors. So we are giving the memory write process control bits, given the read bit lines, and the same time we get the control bits for the SRAM. The standby power overhead is the 70 large area overhead of the 7 process. and then the write and read output, we get the design down, we get the process output, and increase the 70 SRAM applied the voltage back scheme, and can be the write operations is performed every write cycles. In addition, standby power increase because the 70 cache cells using the additional RBL for the read operations. In the 70 cells have been the design that to improve the RSNM, the resolving of the row of select issues using the vertical and horizontal word lines. In the process, we have dynamic power overhead back operations, and then we the final simulation the process, we have get the output from the graphically process, and we denote that result performance in the analysis of the process in the SRAM cells and the memory allocations. Now we are going to discuss about our product training processor. So in this our tool for the Tanner tool, and then we have designed the process. First of all, we have to create our product designs. Just we have to go to the file and new the designing the new design the process. So whatever maybe we have giving the name for the designing process name, and then which is location we have stored in the process. So we have just to create the folder names, that's, and then we have create the cell process. Just this is the main project of the process designing name, and this is the cell 0. We have split the sheet of the designing sheet, cell 0, cell 1, whatever. Then so first we have going to the new cell created. I have already created the cell 2, and then we have just denoted the cell 3. So whatever main name we have separately we give it, and then you have to just design the process. After the process is finished the designing, we are going to the simulation setup. In the simulation setup, we have denote the transistor for analysis. Click after this is double click, we set the setting the process. We should give the start time of the 200 nanoseconds and maximum time set for 1 nanosecond, and print start time is 0, print time set is 1 nanoseconds, use initially conditionally false. So what are we have need, we should give it the mode of the process. After the we have given the process, and then okay. After we give it the process, the just we have designed after the setup the starting simulation. After finished, we give the starting the simulation process. The automatically we open the T-space process, and then we get the graphical output for this process. Oh, this is our process output. So cell 0 process. So we have split the output. So this is the read functions. This controller side for the 5 voltages. The both this is the lines is controller sides, and this is the output of the process. This is input connections. This is input bit connections with the read connections. So what are the input we are given the bitwise, at the same time the clock, which clock is enabled, the same time it will be give the output. At the same time is the zeros. So I have given the zeros as 1 0 1 0 1 0 in the, this is writing the bit in the same read bit line. This is a write bit section, and this is a read bit section. In the read bit section we have get the output for the just half of the cycles. So why we have getting this process, because the clock only the enables the process, so we get the output to the this all bit is enabled. This after the sections we get the output for the zeros. Thank you.